Hi friends, in this video we'll discuss about MHD, magnetohydrodynamics and microfluidics with electro-osmosis effect. So this is an very micro in nature, the size and the shape what you are seeing. So for this kind of structure, if the fluid is present and a specific potential is given, if a specific potential is given here, maybe positive for anode and here 0, and due to these positive and 0 values, so what is the net electric field that is generated here? So there will be net electric field that will be generated between these two, right? So if there is a net electric field generated between these two and a magnetic field is applied in the bottom direction, for example, so if I try to apply magnetic field B, that too in only one direction Z, which is 0.36 Tesla, I'm trying to apply this kind of magnetic field, and there is a potential that is given here. So maybe a specific number, and here it is 0. So there are electric field lines that are present here, and these electric field lines are not constant, as it is varying with respect to the space, the permittivity, electric permittivity, it is varying in the space, and this Bz is a constant value which is applied in this perpendicular direction to the plane. So when it interacts with these two, so there is a force called Lorentz force would be generated. Lorentz force would be generated. Lorentz force generation is due to the reason, so as there is electric field, there is a current that would flow from this to this, which is in magnitude I am taking it as an ampere per meter square. So due to this current density, and there is a magnetic field, so when you try to use Fleming's rule, then you will understand what would be the direction of F. F is nothing but the Lorentz force, which is J cross B, so which would be perpendicular to both J and B, and that force will try to rotate the fluid in this direction. So that kind of force will try to have a rotation in this direction. Similarly, near to here also we will see a rotation, because there is a high current magnitude from this to this nearby this, right? But as it is going away, the current magnitude decreases. So there you can see where the current magnitude is more, you can see the rotations which is created due to the Lorentz force. Now for that, we will first need to solve the governing equation, which is for potential del square phi is equals to 0, which is a governing equation for electric potential. So once this equation is solved, minus del of phi would give us the electric field, and minus delta of phi, which is a gradient, so it has two components. One is dou phi by dou x and other is dou phi by dou y. So E would be equals to minus of plus j cap. So these are the two x component, y component of electric field, and now you need to place that electric field in this equation to get the current magnitude that is present here, J. Okay, so once you get J, you can directly use this formula, which is J is equals to sigma minus del phi by del x I plus del phi by del y j plus u cross b. U cross b, u is again has a three components, c underscore u, I mean the velocity along x direction, c underscore v y direction. I am talking in terms of ANSYS fluent, so c w in z direction. So this u cross b, the b is a magnetic field, and the magnetic field has three components, by, bx and bz, but remaining two components are 0, and bz is only one component that is present, and that 2.36 Tesla we are using for this example case. So once you get u cross b, the cross product of these two vectors, right? So once you get the cross product, that cross product will be substituted here, right? Also I forgot this one, dou phi by dou z also would be present, dou phi by dou z, So plus U cross B. This gives the J vector, current magnitude. And once we get that, we'll try to apply in J cross B to get the Lorentz force. That Lorentz force we need to take it as a source term, and that source term should be applied for X momentum equation, Y momentum equation, and Z momentum equation. So finally what we are doing is we are trying to calculate the Lorentz force and trying to apply in the momentum equation, because the momentum equation helps us in order to have this kind of rotations or swirling motion of the momentum of the fluid. So we try to substitute in these three equations as a UDMIs, user defined memory interfaces. I am using it and I am storing in these three terms, and once it is been stored and executed, this starts a momentum in this kind of swirling motion or a circular motion, right? So now what this U slip is, this is electro for osmotic slip. I'll just I'll delete these things. Maybe I'll explain through help of a UDF also once this is done. So if you take this would be glass, and here the solution what I'm using is sodium solution, sodium mixed in the our water, okay, so which forms NaOH, and glass would have a silica. So this silica would turn into a positive, and which tries to attract OH minus in this way. So at the wall there would be SiO plus, and if OH minus will try and come near to SiO plus, because due to this positive ion it will be split the NaOH into minus ion, and these minus ion and positive ions will be sustained near to the wall. And there is a Brownian motion always present for OH minus, you know, right? So Brownian motion which is always present, which will not allow to settle OH minus into SO plus, but instead of settling it will try to always move near to the wall, right? So this is predominant only in the microfluidics or nanofluidics. So near to the wall there will be OH minus and SiO plus, maybe it can be any other material also. I'm taking for the glass right now. So these two ions will be present, and this ion will not get settled due to the Brownian motion. It will move here and there, right? So due to this reason, any fluid which is present near to the wall will not have zero velocity, right? So instead of having zero velocity, it will have this kind of velocity which depends on the viscosity, zeta potential, and the electric field that is being present in the tangent direction to the this surface, because the electric field is due to this tangent direction that is present. We will try to incorporate the electric field as we know here, and this is a epsilon which helps us to calculate the entire U slip in again three directions: X direction, Y direction, and Z direction. So these three would be placed instead of having a zero slip near to the wall, which is regular in ANSYS Fluent, what we do for any other regular conditions. But here we will take it as a no shear rate, or we can say that there is a velocity that is present near to the wall instead of having a zero velocity of the fluid, right? So these three concepts we need to coupled inside an ANSYS Fluent UDF and integrate into the actual simulation to see the effect, right? And the UEF would look like this. So this is the sigma value, okay, electrical conductivity of the sodium solution what I have considered in this simulation. So that would be, it's nothing but this sigma what we have kept here. This is the sigma. So that sigma value have taken it as 12.9, and By the perpendicular magnetic field is 0.36, and the remaining things have been using define adjust loop in order to calculate the potential gradient, and from the potential gradient I am preparing the Jx, Jy, Jz, which are the current magnitude density, which again depends on the U cross B. This is U cross B. This U cross B is defined here, and those three are used for X, Y, Z directions in order to get Jx, Jy, Jz. And those Jx, Jy, Jz again is been placed in Fx, Fy, Fz, which are the Lorentz forces, and those Lorentz forces are saved into the UDMIs, and those UDMIs are being called as a source terms to incorporate in the momentum equation. So this define adjust will be called for every iteration of ANSYS fluid, and with respect to that every iteration we will try to define the Lorentz force and substitute in the momentum equations as a user defined memory. So this is the first concept. The second concept is the electroslip velocity. So that is already stated, electro-osmosis effect. So for that we need to calculate the tangential electric field. So for the tangential electric field, first I'm taking the dot product which gives the normal electric field. So then from the actual electric field, I'm subtracting the normal electric field which gives the tangential electric field. So this is a tangential electric field along XYZ direction. And now I've used this switch methodology. When there is a u velocity, it would take slip for the x direction, which is 0. If that is y direction, then it will take 1 in the y direction. If it is 2 in the z direction. So according to the switch, the position, this position can be I, j, k. So depending on x or y or z, this would be activated and incorporated in the ANSYS fluent simulation. And this is in the defined profile UDF what is being integrated. Okay. So once this is created, I'll just show you the case. It's a simple case. It's not that complicated. I mean the geometry, what I mean to say. This is a simple one, and these are two terminals what I have kept, positive or negative, or it will be one value is positive, another value is 0, and this is my sodium chloride mixed into the water, and the density and conductivity and viscosity, this is the metal properties I have taken. Then after I am using the turning on the potential and electrochemistry on, for the potential governing equation need to be solved, right? So for that equation, so this is the governing equation which need to be solved. So for that I have activated potential electrochemistry. Then for anode, which is this is the anode, I have given a potential source which is 0.4 volt I have applied, and then for cathode I have taken it as 0. So for cathode it is 0. Okay. So then we need to hook the UDF. So we will go to the function, go to compile. The same UDF I can just load it. For your case you need to build and load it, and you will get this Lorentz forces and electroslip velocity. So you need to go to function hooks and use the define adjust, add it here to hook that, and then you should go to the cell zone condition in the fluid, turn on the fluid, and in that you need to activate the source terms. So go to source terms, x momentum, Lorentz force x, and the y momentum, Lorentz force y, and the z momentum, Lorentz force z. Close this. Then what are all the walls present? I'll select these are the walls. In the walls, instead of stationary wall, I'll give it as a moving wall with the components. So which is not, I mean, same like giving the slip velocity. Instead of specifying the shear, I'm giving the velocity near to the wall. These are the way you can do. So same UDF you can keep for all these profiles, because it is neither less same. We are using the switch case statement. Depending on the I, j, k, it will give the x component, y component, and z component. So then click on copy. You can copy to this two other walls also. Yes, close it. Now you can just increase the memory locations we are using. So it's already increased. So you can just initialize and run. And taking this as the time step size. I'll just stop here so that I can show you like what's going on. We'll select the two planes and check what is the pressure rise or how it is getting distributed. Right. And velocity. So you can see here, so you can see there is a swirling. Maybe I'll show with the help of particle tracks. You'll understand more in deep, sorry, path lines. So you can see here there is swirling effect, right? So hope I have made the sense to you how exactly it look like. So maybe instead of having the two planes, you can create one plane, then you understand how the swirling is present, right? Then we can also check the potential. So you can see here the potential, okay? And if you want to check the Lorentz forces also, we have this thing how the Lorentz forces are acting. So you can see positive, negative, positive, negative. This is swirling the things due to the forces that are acted due to the UDMS what we have framed by the governing equations, right? And in the potential you can also see the current density magnitude. You can see here this is the density of the current that is present. And again in the path lines also you can check how exactly these are varying. Instead of having that, you can check that potential also, or else you can check the current density magnitude. It will show how the current is flowing from one electrode to other electrode. It will take some time. So basically this is an application for microfluidics. So macro and those things, then it will come in different wave. There will be no slip velocity. So here in this case there is a slip velocity near to the wall. Okay, so the velocity is not zero, which is like a no slip condition. So you can see there is a current that is flowing from one electrode to other electrode. I'll just turn on the sixth plane, then you'll understand more in proper sense. Which is in the YZ plane, what I'm trying to show now. You can see here the current how it is going, and then due to the swirling it is swirled, and again it is coming here. Okay, so this is how you can just play with the things. You'll understand more in deeper how these Lorentz forces that are coming due to the variable electric field that is present in the space when you apply a constant magnetic field and all those things, right? And you can also have a different magnetic field variabilities in XYZ levels also. I hope this video has helped you a lot in understanding this electric and magnetic into hydrodynamics. And yeah, so if any questions or queries, you can just drop a mail to the mail ID link.